Is AP Physics C, and I am going to give an overview of Unit 3 on work and energy in the AP Physics curriculum. In this unit, we are going to talk about four things. One is the work and energy theorem and the connection between work and energy. Forces and potential energy, connection between force and potential energy. Conservation of energy and the powerful nature of using that, and power. First of all, work. Need to be able to understand the definition of work and how to calculate that. And so understanding both work from a constant force aspect, where your work is the dot product of your force times your position vector. It could be in any direction. I'm going to use x here to help you. Which is your F times x times the cosine of the angle between the two. So this is your dot product of the work that ends up being a scalar. So work is by a constant force. You can just do this. But if you don't have a constant force, if you have a function force, then work is the integral of your force function. So some force is represented by a function of position times your dx. These are also vectors, and take the integral of that to get work. So whether it's a constant force in the first one or a changing force in the second one. In both cases, it produces a scalar product when you take the dot product of two vectors. You should understand what positive work is versus negative work. So positive work is when the force acting on it in a direction is going to increase its speed. So it's working in the same direction of the movement. Or negative force is when it's working in the opposite direction of it. Examples of negative work would be if you're lifting a ball up and you're going against the gravity is going against it. That would be a negative work. Or if you're pushing a box on a table, friction would be in the negative direction, and that would be work on that. And then if you had a diagram or a graph of force and position, you should be able to get work from that. And so, for example, if I take my force versus position here, and we apply a force for a certain amount of time here, you can calculate the work by getting the area under the curve. Work and energy, and you do that by an integral as well. Work and energy, then the connection between work and energy. Well, if you do net work on things, and this is including all of the forces acting on an object, what is the net work? Is going to result in a change in kinetic energy. You can change potential energy, you can produce heat as well with work, but the net work is going to produce a change in kinetic energy when you consider all the forces. And if we can remember what kinetic energy is 1/2 mv squared, and the dependence on speed that you have here, at least with translational kinetic energy. We have other kinetic energies that we deal with in this class. If it's a single force, then the work is just going to be the force times distance. But if you have multiple forces, you could have positive works, you could have negative works. When they all add up together, the sum of those is going to give you a change in kinetic energy. So like a work of a push, for example, could result in some other form of energy. It could change your potential energy, or it could produce heat depending upon the situation. For example, if you push something up an incline, you have gravity as a negative work on it, but your push is going to produce a change in potential energy. Heat will be produced if you push something against friction. But friction is a negative work, so in the end, you may produce zero kinetic energy, no change in kinetic energy, because of the net work. But a particular value of work may give you a change in energy. Potential energy and conservative forces. So we should explain the connection between potential energy and some sort of conservative force. So your potential energy is the integral of your force times dx. Okay, so that's the integral of that. An example, you could say, what if my force was mgy, which is gravity force, right there? Oh no, if my force was just mg, which is a gravity, negative mg, my potential energy, take the integral of this, is going to be mg times the change in y. So whatever my height change was, because h is my position vector times the force, which is mg, and you get to this value right here. So you should be able to represent that. Also, the opposite directions is if your force is going to be the derivative of, and that should have been a negative right there. The force is the derivative of your potential energy with respect to position. Okay, and this is for conservative forces. I did not mention the conservative forces. Conservative forces are where if you go one direction, you can return it the other direction and you bring back the energy. For example, lift something up onto a table and then bring it back down. That's a conservative force. Gravity acting on it is a conservative force, and it's not going to lose energy. However, if you push something against friction, if you push it one direction and then you come back the other direction, you're adding energies, and it's not a conservative force. Right, and then the potential energy graph. If you have a potential energy graph of U versus X, let's take a spring example here where we would have a parabola or something like that. At some point, we give it a certain amount of energy. The energy of this system is going to be the same throughout. You may have, at this point right here, you have all potential. At some other point, you're going to have some kinetic, and you're going to have some potential. The potential and the kinetic are going to add up to the total energy, which is the blue line. But then you would have that. In a potential energy curve, the force is represented by the slope of the line, or the negative slope. So over here in our equation over here, if it's in the case of this is a negative slope, but it's going to give a positive force, which means it's going to accelerate it in the positive direction. But once it crosses the minimum right here, then the force is in the negative direction, and it will slow it down until it gets to this spot, and then it will turn around and return. Turning points are when the potential energy equals the total energy equals the potential energy. That's where you're going to get turning points. Your maximum speed is going to be at minimums of the potential energy curve. And so you should be able to figure out all of these different things for that. Specific examples, springs. You should know springs. Now we have Hooke's law. The force on a spring is related to your position. It's negative kx. This is for an ideal spring. If it's not an ideal spring, it could be kx squared or something like that. So that's a nonlinear spring. But for a linear spring or a ideal spring, you would follow Hooke's law. In this case, the potential energy is negative the derivative of this, which is 1/2 kx squared. And so you should be able to use the application of energy from a spring in all of these things. So the potential energy of a spring is that parabola that I would have. You can see that it looks like this. 1/2 kx squared would be a function for a parabola, and you can get all of these things there. A linear spring, you would have a different force. You just take the integral of that force to get your position. So, to get your potential energy, you do the integral to get the potential energy, and that helps you get those things. So springs need to be able to do those. And then gravity is the other one. In near Earth gravity, this is where your force is just mg. Now, in the AP Physics curriculum, it says that we should also be able to do it for a satellite system or a moon system where you're far away. In that case, your force is going to be given by a different function, which is using universal gravity, which is gm1 m2 over r squared. We have not talked about this, and I would be very surprised if they use that, but it does say that it's a potential to be used. If that's the case, your potential energy from this force is going to be gm1 m2 over the distance between them, r. Conservation of energy, very, very, very strong thing that you can use to solve a lot of questions. So describe physical situations where the mechanical energy converts from one to another. Drop a ball, goes from potential to kinetic, in a spring, in all of these different situations. And we can see what some examples are in there. So describe the physical situations in which the total energy changes. So there are some cases where the outside source is giving energy, and when the energy changes, you have work being done on it. And so in the first case, you may just have converting energy from one form to another. In the second case, energy is being added or taken away from that. Calculate the total energy of the system. You need all the kinetic energies and all the potential energies. Calculate all of those, and you may have multiple kinetics or multiple potential energies that you are dealing with. Use work to determine the total change in systems to be able to figure that out. So the work is the connection between energy changes. So pendulums, roller coasters, frictionless ramps, those things. Let me just do a pendulum example. If you have a pendulum that is at an angle of theta here from the horizontal and it swings down, how fast, and it has a length L, how fast is it going when it reaches down here? That could be a question. Well, you have potential energy to start. You have to figure out how high this is to get your potential energy, mgh, and then at the bottom you're going to have kinetic energy, which is 1/2 mv squared. So set those two equal and you can solve this question. So those are examples of using energy. Finally, calculations of conservation of energy. So calculate any unknowns. You could need to know speed at the bottom, as I gave you, position or height or things like that, maybe position in a spring, things of those natures. Be able to calculate those unknowns. Atwood's machines, masses and pulleys, string combinations, springs, examples of where you would have to calculate some part of it, and you can use energy concept to do that. If it's a non-constant force, you may have to use calculus to be able to calculate some things. For circular motion, vertical circular motion, where you're going up and down, that you would need to know the height, the angles, the speeds. Those could be unknowns that you are trying to find. And then finally, power is this. And we didn't talk a lot about power, but power isn't. These are the two formulas you need. It's not that hard. It's the rate at which energy is being done, the rate at which force is doing work. You could think about it in different things, but there's two main formulas that you need to know. It's the derivative of your energy or derivative of your work versus time instead of position. And then the power is also going to be the force times the velocity at which it's being applied. And so force times velocity, you can also think of power in terms of those concepts as well. For example, power to raise an object or lower an object. These could be examples of that. All right, that's it. We will go through examples of this in